Hi, I'm Jeremy Feynman, and I'll be talking about single source shortest paths with negative real weights. Considering the classic single source shortest path problem here, where we're given a graph with edge weights that are allowed to be negative and some designated source vertex, this vertex S over here, and we'd like to compute the shortest distances from S to every other vertex, which I've indicated inside the vertex. I'm going to be assuming throughout the talk that there are no negative weight cycles, but the algorithm is also able to discover these cycles if they do exist. Um, so that's the problem. Let me start with a bit of background. The shortest path problem has a pretty long history, but I'm only going to be highlighting a few things here. Throughout the talk, N is what I'm using to denote the number of vertices in the graph. M is the number of edges, and the O tilde notation hides log factors. So the classic solution for the general case of real weights that can be negative is due to Bellman and Ford, which has a running time of Mn. Um, For the case that the edge weights are non-negative, you can do much better using Dijkstra's algorithm coupled with Fibonacci heaps, giving a nearly linear runtime. Uh, so these are probably the algorithms that most of us are familiar with already. In the case of real weights that can be negative, Bellman-Ford was the best algorithm. But there has been significant improvement when we restrict the weights to be integers. Um, and here I'm just going to list the best bounds. Recently, in the past couple of years, there are a couple of algorithms that have been discovered with a running time that is nearly linear when the weights are integers. Okay, and all of these algorithms use some sort of scaling or approximation technique where you're getting very, very close to the actual distances, like an additive error less than 1, which allows you to compute the exact distances, but only for the case of integers. In this work, I have come up with an algorithm that has a running time of m times n to the 8/9, so slightly beating the Bellman-Ford algorithm, and it applies to the case of real weights as well. Now, when we're talking about these algorithms as working for real weights, we have to be able to compute on real numbers. So the model here is typically a real RAM. And specifically, I'm only assuming that you are able to add and subtract and compare edge weights in constant time. So just doing the normal things you expect to do in shortest path algorithms. There's no like clever algebraic tricks or anything like that. Okay, so there's a couple of tools that I'll be using. The first is price functions, which are attributed to Johnson. The idea is to modify the edge weights without changing shortest paths. So we'll use some function on vertices that assigns a number to each vertex and define a new weight that, so the weight of phi of the edge is the original weight plus the price of the source minus the price of the target. So given this example graph, which is just a simple path, if we use this price function here, then the new weights would be as shown here. Now, the nice thing about using a price function in this way is that if we look at the weights along a path, you get this nice telescoping effect where the weight of the path is, in the reweighted graph is the original weight plus the price of the source minus the price of the target, which in this case would be 0. But it's always plus phi of A minus phi of E here. So the shortest paths will remain shortest paths. Any comparison between path weights is preserved across reweighting. Okay, now Johnson's strategy involves trying to come up with a price function where this new weight is non-negative, which if you just flip things around is saying that the price of V is less than the price of U plus the weight of the edge. And this is a triangle inequality. Shortest paths obey the triangle inequality. So his observation is just that you can use shortest path distances to get a price function that will give you non-negative weights. So you do this by adding a super source to the graph with a weight of 0 to every other vertex, compute single source shortest paths from that super source, reweight the graph according to those distances, and those distances are all non-negative now. The weights are all non-negative now. Now, using Bellman-Ford algorithm to do this, your running time would be mn. We're trying to do the same thing, but faster. So we're not going to be just using Bellman-Ford to achieve this. Okay, so the general strategy is going to be to try to do this more gradually, but hopefully more efficiently as well. So I'm going to start with a graph that has some weight function. Uh, some of these weights will be negative initially. I'm showing all of these negative weight edges as being red in my pictures. Negative edges are those that are initially negative. The negative vertices are those vertices that have any outgoing negative edges. So these two vertices in this picture. And I say that a price function eliminates a negative vertex if all of its outgoing weights become non-negative. So if I weighted the graph to produce these new weights here, this yellow vertex now has only non-negative outgoing edges at this point. So it has been eliminated. So we'd like to gradually eliminate the negative vertices somehow like this. And also, of course, do this in a way that doesn't make anything else worse. So the non-negative edge weights should remain non-negative throughout the course of the execution. Okay, so that's going to be our general strategy. Here's the main result of the paper. Consider a graph with k negative vertices initially. Then I claim that there's a randomized algorithm that eliminates k to the 1/3 of the negative vertices. And it does so in time m times k to the 2/9. Once you have this main algorithm, you can just repeatedly execute it until no negative vertices remain. And in doing so, you'll get a running time of m times n to the 8/9. And then finally, you have a graph with no negative weights, so you can just run Dijkstra's to find the shortest paths. Okay, so that's the main result. So what's the tools to do this efficiently? Well, one of the existing tools is hop limited shortest paths. So I will define a path as an h-hop path if it contains at most h negative edges. This path along the top has 3, so this would be a 3-hop path. Path along the bottom has 2, so it would be a 2-hop path. The h-hop distances are the shortest, the h-hop distances are the weights of the shortest h-hop paths. So in this picture, the 2-hop distance from S to T is this path is characterized by the path along the bottom, which has a total weight or distance of 2. And the shortest 3-hop distance goes along the top here, giving us a distance of -1. Okay, now it's pretty easy to come up with an algorithm that computes h-hop distances. All you need to do is just alternate between doing a single round of Bellman-Ford on any of the negative edges, followed by a full execution of Dijkstra's algorithm, then a single round of Bellman-Ford on the negative edges, then a full execution of Dijkstra's algorithm on the non-negative edges, and keep going back and forth. You do this h times, and this has a running time of h times m times the log factor for Dijkstra's. I do want to note, because it's a little bit subtle and somewhat important, the definition of a negative edge I'm using throughout the talk in the paper is the edges that are initially negative weight. It is possible that the algorithm will change some of the edge weights along the way to make them positive, but I still want to call those negative edges. And the reason I want to do that is I want the number of hops along a path to remain consistent throughout the execution. So when we reason about like h-hop distances or h-hop paths, those paths are invariant throughout the entire execution. Okay, so Just want to note that in case you miss it as you're reading through the paper. Okay, so now let me get into the algorithm a bit here. I'm just going to give some of the overview here. A lot of the cleverness in the algorithm really comes down to coming up with the right objects and the right definitions to come up with anything that seems to allow us to do anything. So I'm going to be focusing on these definitions, and I'll give a little bit of a hint of some of the components of the algorithm, but not everything. Okay, so recall that our goal is to reweight the graph to eliminate some negative vertices while keeping all the non-negative weights non-negative. And a general approach is going to be to find some sort of easier subset of vertices. So if this is my original graph here that has 4 negative vertices, perhaps I can identify that these 2 yellow ones are a little bit easier. So I'll drop the other negative edges from consideration, and then I'll try to come up with a price function that eliminates the yellow vertices. So now I have a subgraph that has no negative weights. And then we can add back in the missing edges. But we now have fewer negative vertices when we do this. And then just go back to the beginning and restart the algorithm again to make more and more progress. Okay. So the real question is, what's a good subset of vertices? What's something we can find efficiently and eliminate efficiently? So the first case is an independent set. This is the easier case. So let me start by defining this. So I say that 2 vertices are 1 hop independent if the 1 hop distances between them in both directions are non-negative. So both B and D are 1 hop independent in this example because the distance from D to E is positive and the distance from B to D is also positive. I claim that you can eliminate such vertices in linear time. And you do that basically just by running Johnson's algorithm. So add a supersource and compute single source shortest path distances. But the observation is that to get the shortest paths, we don't need more than 1 hop. And this is because there's no reason to go, say, from S to B to D and then continue to something else, because we may as well just go directly from S to D, since the distance from B to D is non-negative anyway. Okay, so that's a really easy case. But I don't have any idea how you would always find a big independent set. So we need sort of another option that we can find instead. And the other option is what I'll call a remote subset. Okay, so let me get to how do I define that? Let me start by defining the R-hop reach of a vertex as the set of vertices reachable by negative weights R-hop paths. So if we focus on this vertex U on the left here, these are the vertices that I can reach by negative weight 1 hop paths. So that's the 1 hop reach. These are the vertices that I can reach by negative weight 2 hop paths. Okay. I say that a set of vertices is R remote if the size of their collective reach is at most a 1 over R fraction of the graph. So in this picture, this is the entire graph, and these 3 vertices are R remote, then they should have a reach that only reaches a 1 over R fraction of the graph. Okay, now why is this notion of a remote subset useful? Well, I claim that, let me focus on the second bullet here. I claim that if we're given a graph with k hat negative vertices, and those vertices are all R remote, then there is a deterministic algorithm for single source shortest paths with a running time of k hat m over R. So this is a factor of R better than Bellman-Ford. Okay, and I'm not going to give you this algorithm in the talk. You can go and look in the paper. I don't think that it's obvious, but it's also not hard. But let me just give you some intuition here. The idea is that most of the work you're doing when you're computing shortest paths is restricted to the R-hop reach because you have to go pretty far before you have to take a lot of hops before you get to negative paths that sort of leave this region. It's a little bit more complicated than that, but Just suffice it to say that most of the work you're doing is in there, so you can save a factor of R in the running time. Okay, so since all we need to do to eliminate vertices using Johnson's algorithm is compute single source shortest paths, this means that if we have an R-remote subset, we can eliminate that subset by just running single source shortest paths on the subgraph. Now, given the various running times of components of the algorithm, it'll turn out that the best choice of R is k to the 1/9. So you can keep k to the 1/9 in mind for R throughout this talk. Okay, so far, our goal is going to be to find a big size k to the 1/3 one-hop independent set or R remote subset, and then to eliminate that set, meaning that all of the outgoing edge weights should be non-negative. But finding these sets is really the hard part. And in fact, they don't always exist. So here's an example of a graph where there's no non-trivial independent set because every negative vertex is one hop related to every other one. And there's no non-trivial R remote subset either because every negative vertex can reach this entire part of the graph that's on the right-hand side, which could be most of the graph. Okay, so here's the general structure of the algorithm. We're going to do a few extra steps to try to manipulate things into producing the remote subset. So first I'll start with this component where we reduce the betweenness. Then we're going to search for either an independent set or something I'll call a sandwich. If we find a sandwich, we can then reweight the graph to make it so the sandwiches are remote. And if we find an independent set, we can just eliminate it using the algorithm I already talked about. And then once we have an R remote subset, we can eliminate that as well, which is something I mentioned already, but I'm not going to give you the details in the talk. Okay, so I really want to focus on these first two boxes here because the definitions and the structure here are really the important part. This reducing the betweenness is only used for this third step of making a sandwich R remote. But I think these definitions for these first two boxes are really where most of the cleverness lies. Okay, all of the blue boxes here involve reweighting the graph. So there's several places in the algorithm where where reweighting occurs. And the places where randomization occurs are this first box and this third one as well. Okay, so let me give you one of the key insights, I think, to sort of start making progress here. And this is thinking in terms of the distance through some other vertex. So I will call the beta hop distance from U to V through X, or the through distance, denoted this way, as define that as the distance from U to X plus the distance from X to V. Okay, so we're forcing you to go to X along the way. For example, in this picture, the distance through X will force me to take this path along the top, which has a total length of 8, and the distance through Y will force me to take this path along the bottom, giving me a length of -6. I say that a vertex is beta between U and V if the through distance is negative. So the distance through X is non-negative, so X is not between U and V, but the distance through Y is negative, so I say that Y is between U and V. Now the betweenness of U and V is just a number of vertices that are between it. So then the number of vertices with negative through distance. In this picture, that would be every vertex in this bottom half of the graph has negative through distance between X and V, or between U and V. So there are 5 vertices between U and V. Okay, so that's betweenness. And as I mentioned, the first component of the algorithm is to reduce the betweenness. And I claim that that there's a randomized algorithm that has a running time of R squared n that reweights the graph so that the betweenness for all pairs of vertices is at most n over R. So why is this true? Well, let me start with the observation that through uh, the through distances have the same ordering across reweighting. So if the distance through X is bigger than the distance through Y before reweighting, it is also bigger after reweighting. And you can see that just by looking at the example graph. If this is my original weights and I reweighted the graph, in this case, I just added 9 to all the weights coming into this last vertex. The weight along every path from U to V has increased by 9. So the distance along the top is still bigger than the distance along the bottom here. Now, once we observe that these comparisons are invariant, it's not hard to come up with an algorithm to reduce the betweenness. And the idea is just to sample R log n random vertices and then reweight the graph so that the R plus 1 hop distances to or from the samples are non-negative. Now you can do this by basically running R squared log n hop shortest paths. It's not really that hard to do this, so I'm going to sweep that aside. But what's the idea here? Well, you're likely to sample from among the n over r smallest through distances between U and V. And as long as you do, those distances by construction, the through distances from a sample become non-negative, as do any through distances that started larger. So the only vertices that can remain between U and V are those that had the smallest through distances in the beginning. Okay, let me introduce the second object here, which is the sandwich. I'll also talk about the independent set again. And here I want to think about the one-hop relationship graph. So if we have our original graph here, I'm going to build a relationship graph on the negative vertices in the original graph by adding edges between vertices in the relationship graph if there is a one-hop path of negative weight in the original graph. So here there's a one-hop path from C to A that has negative weight, so I'll put an edge from C to A here in the relationship graph. Okay, now the two objects we're searching for are either an independent set, which is a subset of vertices that are not neighbors, or a sandwich, which is some vertex X, some vertex Y, and some set of vertices between, where every vertex in between has an edge from X and an edge to Y. So this would be an example of a sandwich here. Okay. I claim that every K vertex graph has a pretty big independent set or sandwich. And it's not too hard to come up with a deterministic algorithm to do this, to find one constructively. Now, we can't afford to actually build this relationship graph explicitly, but you can use some random sampling and one-hop single source shortest paths to get the same effect by doing something in the original graph. Okay, so I'm not going to go into detail on how that works, but that's the idea here. So putting everything together, this first component has a running time of r squared m. This last component has a running time of k to the 1/3 m over r. And these running times end up dominating all the other components. So we can minimize the total running time by setting r equals k to the 1/9, which gives us this running time here. Okay, so in conclusion, we solved the single source shortest path problem with real weights in order mn to the 8/9 time. This is probably not the final answer, but the main point is just that it's possible to beat the Bellman-Ford bound at all. There are two obvious main directions for follow-up work. Obviously, we can try to improve the running time further. It might also be nice to come up with a simpler or more natural algorithm that doesn't involve so many steps. I think that would be a nice contribution as well. I am pretty sure that it is possible to beat this bound, but I don't have any sense of what the best bound is. It seems like using this technique, the best you could hope for is m times n to the 2/3.